Hello, welcome to Chapter 7, Section 6, which is called The Natural Base E by Dr. Berger and his crew who wrote the book. In the previous video, I gave the background into where this special number kind of comes from. And in this video, we're going to explore that number a little bit more and talk about what it actually means. Let me grab another sheet of paper. I'm going to come back to this in just a second. Okay. This number allows us to do incredibly complex math, which you're going to learn about. Again, my job is just to introduce it. That's all that we do. We talk about it for this section, and then that's it. We move on to something else. You will go a little bit further when you get to pre-calculus, and then you start to do some complicated problems in calc, and this will it'll make things go a lot easier. Of course, that's not much help right now. So let me just try to explain this, okay? Because we have 10 fingers, or at least that's what the belief is. That's why we have what we call a base 10 numbering system. So, for example, if I had 4,732, that becomes 4 times 1,000, which is 10 to the third power, plus 7 times 100, which is 10 to the second power, plus 3 times 10, which is 10 to the first power, plus 2 times 1, which is 10 to the 0 power. And of course, if I had decimals, then I would have, like if it was 0.3, then I would have 3 times 10 to the negative 1 power. We've been learning about this for a while. I introduced it when we were talking about polynomials because a polynomial looks like this: 4x cubed plus 7x squared plus 3x plus 2. This is just one type of polynomial where we're using an actual constant instead of a variable. Okay, but let me get back to this. This is probably because humans counted on their fingers. Okay, so every time I ran out of fingers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, every time I ran out of fingers, I had to grab somebody else and say, all right, every time I get to 10, you hold up one finger, and that's going to stand for 10. And when that person ran out of fingers, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, I had to grab somebody else and say, okay, that's now 100, so forth and so on. That's probably the way it works. At least that's what we think. Well, we humans are pretty smart, to be honest. Computers don't do this. I want to borrow computers for just a second, borrow the idea of computers. Computers only work with on and off. So a number to a computer would be like 1, 0, 1, 0, 1, 1. So that'd be on, off, on, off, off, sorry, on, right? And what this would be, and I probably went too many places, but 0, 1, 2, 3, 4, 5. Okay, so this would be 1 times 2 to the 5th power, plus 0 times 2 to the 4th power, plus 1 times 2 to the 3rd power, plus 0 times 2 to the 2nd power, plus 1 times 2 to the 1st power, plus 1 times 2 to the 0 power. So the computer would never do this. We have to do this as humans. We have to do this to understand what the computer's doing. And if I think about this, humans are way smarter than computers. We can take this number and figure out what it is using our base system. Okay, so like, to me, I'd say this is 32 plus 0 plus 8 plus 0 plus 2 plus 1. So that'd be 43. This is how I would write 43, the number 43 in base 10. I don't think computers know about 4s and 3s and base 10s. So I think from human to computer, we can do that. But I don't think computers can go the other way. As a matter of fact, I think that the whole reason why software engineers have to write code is just translating computer thoughts into thoughts that humans can have, and vice versa. It's just translating what we want to the way computers understand it, and having computers give an output either through a screen or a printer in ways that we understand it. Kind of got deep and philosophical there. I have a good friend who's a computer scientist, so I'll ask him how close I am to that. All right, now you probably wonder, what does that have to do with anything at all? Well, this is base 2, because you've only got two things, ones and zeros. This is base 10, because I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. With the 0, I've got 10 symbols that I can use. So that's base 10. Well, we can do something that's called base E. That's that E again. And just like maybe computers don't understand base 10, we have to write code for them to translate it that way, I think it's kind of hard for humans to understand base E. If I wanted to write a number in base E, and this would not even come close to being the way it is, just kind of like, because I'm actually going to be using base 10 numbers in this, but I would have some number like 3 multiplied by e to the third power. And I would have some number like 7 multiplied by e to the second power. And then I'd have some number like, anyway, I would have some number like 5. 7 would have been a bad choice, but it's okay, you're not going to know that for right now. Times e to the first power, and then some number, say 1, e to the 0 power. So like I would have base 2, base 10, I'd have base e. And the thing is that I think humans, it's hard for us to understand numbers in base e. But this is what we would be using if things occurred naturally. Or if you want to get religious with it, like this, and I thought this was a cute way. I had someone say this one time. Computers think in base 2, humans think in base 10, God thinks in base E. Okay, mind blown. All right. And of course, I don't need to get any emails, talking about, like I mentioned, religion. It's just a poetic way of saying it. Okay. This base system makes a lot of the math that we're going to do easier. And I know at this point it's really hard to understand that. But just, man, as you guys start your journey and you start learning about more and more advanced math, just keep coming back to that. Whenever you see E and the natural logarithm, which, spoiler alert, that's the logarithm with base E, when that comes in, think about that, okay? And of course, and here's why my explanation, I'm using base 10 numbers, just like I use 2s here, to kind of describe it. Because again, this is what humans think in. So I have to think base 10 here, and I have to think in base 10 here. But at least, hopefully you get the idea. Okay, enough of that. Let's talk a little bit more about this wonderful number e. So e is the base of an exponential function. If you grab your calculator, let me hit clear. Right here where it says ln, and that stands for natural logarithm. I'll explain why it's ln in just a little bit, okay? We're only going to talk about the exponential power. Right in blue it says e to the x power. So here's what I'm going to do. I'm going to do second. So I'm going to get e to the x. You can see it right there. And I just want e to the first power, which just gives me e. And this is an approximation, 2.718281828. It kind of looks like it starts to repeat a little bit. It goes 1828, 1828. So maybe it repeats. It does not repeat. That's just a cool little quirk, okay? This is an irrational number like pi, which means the decimal goes forever, and I mean forever, like forever and ever and ever and ever and ever and ever and ever. Okay, and you're probably just getting bored hearing me say forever, and I only did it for like 5 seconds. I mean, and not like millions and millions of years from now. I mean, beyond that. It's kind of mind-blowing. But like pi, we usually estimate it. This I stole. I think I stole it from Wikipedia. I had to look it up. This is to like, I didn't even count how many decimal places I got, but you can count it. Just pause the video and count it. And hopefully I copied it right, because I was like going from one screen to another screen. But again, with the ellipses here, this means that it goes forever. This is what the value is. For our purposes, for what we need to do, you can just say it's just a little bit bigger than 2.7. And if you want to go 2 decimal places, you can say 2.72, because the 8 makes the 1 round up. Okay, this is closer to 2.72 than it is to 2.71. All right, we don't just cut stuff off. All right, so what are we going to need to know for this video, for this example? Well, all we're going to be doing is we're going to be graphing the exponential function of this. All right, so this table right here, have this written down somewhere. All right, here's what's important. Any number to the 0 power equals 1, except for 0. So e to the 0 power equals 1. And like I just showed you on the calculator, e to the first power is 2.718. Of course, it's 2.7183 is what it's rounded off to, because the 8 makes the 2. It's closer to 8.3 than it is closer to 8.2. So that's been rounded off. And then if I do e to the second power, I get 7.389. And whoa, I wonder what happened there. I must have copied something wrong. I'll tell you what. Here's what I was going to do. Let me see if everything's okay. So I'm going to do y equals, and I got e to the x power already put in there. So I made a table. I might have copied it wrong from what I had. So 1 was 2.7183. Got that. And then, yeah, I don't know what I did. I just wrote it wrong. Let me fix it real quick. There's actually 7.3891. Okay, I wrote a 5 instead of a 9. That's what it was. Okay, sorry about that. And of course, 20.086. All right, what's important? We're going to be doing some graphs. So let me show you what the graph is going to look like. I've been setting this up for a while, just so you guys know. This is y equals e to the power of x. And the things about this graph, don't be confused about. First of all, you're going to know right here, this is 0, 1. Just like the exponential function 2 to the power of x, 10 to the power of x, any number to the 0 power equals 1. So when you graph this, or when you look at graphs, without multiplying the whole thing or without doing translations, which comes up in a later chapter, okay, so I'm not going to lie to you, we're going to do translations and stuff, but if I just look at this one without doing any transformations of it, then x equals 0, e to the 0 power equals 1. So we're going to go, the y-intercept is going to be at 1. And this next point, x is going to equal 1, and then this is going to be e. And of course, that'd be the same as aka, also known as 1, and we can say 2.7. And when we look at the graph, I'm not going to go to that many decimal places. All right, it's going to be hard enough just to go to like 7/10. That's like slightly more than halfway. So if I zoom in real, and I can't do it because I'm using paper, I can't like that, all right? But if you can see where my grid lines are, here's 1, here's 2, here's 3. So this is between 2 and 3. It's more than halfway, but not quite 3. And there's going to be no way that if you drew this by hand that I'm going to know that I'm actually going to be able to tell. I'm not going to be like, oh, it's off by a millimeter. I'm not going to do that. But I just want you to know that this point right here is 1, and then about 2.7. What is this point right here? Well, again, it would be good to remember this. This is about 7.4. So this is 2 and about 7.4-ish. So those are estimations. What about over here on the side? You don't need to worry about that. Why? Because of what we've talked about with exponential functions throughout the whole time. This goes vertical, this goes up, but never perfectly vertical is what I started to say. So notice that it still goes to the right, just like every other exponential function that we ever do. And if I graph this, TI-84 is a bad graphing calculator. It doesn't show what happens here. Desmos does just a little bit better. This is what I screenshot from. What happens on this side? It goes up but not perfectly vertical. What happens on this side? It comes down to the x-axis. This is the x-axis. This is the y-axis. It comes down to the x-axis, but even though you can't tell because of my printer, it never, ever, ever equals 0. Notice that it's getting smaller and smaller, but it never actually equals 0. Okay, so how does that help? Well, let's do one example. Sorry, I was trying to turn my calculator off so the batteries won't die. All right, we are going to graph the function f of x equals e to the power of x plus 2. You got this. So I'm going to take these values right here, and I'm just going to add 2. And I'm just because of the spacing, I'm going to write it vertical, right? So this is going to be my x value. And I'll do -3, -2, -1, 0, 1, 2, 3. Now, I can keep flipping back from that one to this one, but I'm just going to save myself some time. I'm just going to write something down here. I'm going to write e to the power of x. That's what this one is. So e to the 0 power equals 1. I'm going to put 1 right here. E to the first power, like I said, is about 2.7. I'm just going to say 2.7 because I don't need to go multiple decimal places just to graph it. And then to the second power, I get 7. I'll round it up to 7.4, and this is going to be 20, 20.0. 7.4 and 20.0. Mine only goes up to 10, so I don't even need that, right? For the negative exponents, it's going to be the reciprocals of those, which again, I've just figured out using decimals. So this will be 0.37, this will be 0.14, 0.37, 0.14, rounding off, and this is going to be 0.05. Okay. I can graph that if the if the directions, I don't know why I said calculator, if the directions said graph both the parent function e to the x power and then graph this one, I could do it, but I'm actually only going to graph this. So now I'm just going to do e to the x plus 2. So I'm going to take all of these numbers, I'm just going to add 2. So I get 2.05, 2.14, 2.37, 3. 1 plus 2 equals 3. This is 4.7. This is 9.4. I don't know why. I pretend I wrote a 4 to begin with. And this is going to be 22.0. So I take my parent function and I just add 2 to each of these. If it was and we'll do this when we get to the guided practice problems later. I think we have 4 of these to do. So sometimes we're going to add, sometimes we're going to subtract, sometimes we're going to mess with the x. Those are going to be a little bit harder, but don't worry, I'll show you how to get through them. Okay, so let me graph this one. So again, this is my x. This middle column, you can please ignore. That was just my temporary scratch work. I'm going to go 0, 3. 0, 3 is right here. So here's, yeah, look at it sideways, okay? 1, 2, 3, right here. And I don't know if you can tell, but I'll make the marks in there and make it easier for me, actually. This is a screenshot from Desmos, so I could like put the graph the way I want it instead of just like the normal graphs that I usually steal from the worksheets. And because I did it that way, the grid lines don't always show up. Nice. Okay, so that's why I put them in. So that's 0, 3. 1 gives 4.7, so I'm going to come over to 1. I'm going to go 1, 2, 3, 4. Here's 5. I don't want to go all the way up to 5. I'm going to go slightly more than halfway. And notice I'm not too picky about, well, okay, that looks like it's halfway. You're fine. It's okay. Don't panic about that. Just, it's between 4 and 5. Probably closer to 5, but again, I'm not going to panic about it. 2 goes up to 9.4. So here's 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's 10. 9.4 is really close to 9.5, which is halfway. So if you put it right there in the middle, that'll be okay. As a matter of fact, because I made a big thick dot, excuse me, because I made a big thick dot, I probably covered everything from like 9.3 all the way to like 9.7. So it's okay. We're just going to estimate. Going back the other way, 2.37, if I go over to -1, I go up to 2, and I go slightly less than halfway. And then 2.14 is a little bit higher than 2, and 2.05 is also a little bit higher than 2. And when I connect these, I do it, try to make it with a nice curve. Not perfectly vertical. Yeah, that's one of my better graphs that I've drawn. Nice job. Now I want to point out one thing. We're done with this problem. I graphed it. I want to point out one thing. This is covered in another section, but I'm just going to mention it here. This adding 2 is what we call a vertical translation. The graph of the other function, the one I did on Desmos, got pushed up. Everything got pushed up 2 spaces. So it's a vertical translation up 2. Not only that, but like, well, let me go back to this one. How this graph never touches the x-axis, well, even that part moved up 2. So this graph, and I'll try to draw it like this. This is not part of the graph, but like the x-axis doesn't move, but the important part about the x-axis moved up. This is called an asymptote. And that'll be important, well, it'll be coming up in a couple sections, but it's a very important idea in math. So this graph comes down close to this line, which is actually y equals 2, but it never touches it. The original function, the parent function, the asymptote is actually y equals 0, which is the x-axis. Okay, so we'll be graphing more of these later, and that's all I'm going to do for this video because it's gotten kind of long. Bye.